Hello everyone, I am Farah Anjum from Sri Venkateshwara College of Engineering, Bangalore. The topic for today's presentation is Design and Implementation of an Open Source Framework and Prototype for Named Data Networking Based Edge Cloud Computing System from the course Cloud Computing. Abstract. The paper explores the integration of named data networking with edge cloud computing as a solution for improving information response times in future internet technologies like 5G. The proposed framework uses a three-tier architecture. Tier 1 connects IoT devices via NDN. Tier 2 includes the edge computing layer with an edge node application. Tier 3 features cloud computing, deploying a cloud node application on Microsoft Azure. The NDN-based ECC framework is evaluated through test bed experiments and simulations, measuring interest aggregation, round-trip time, and service lookup times across different traffic loads. The findings suggest that combining NDN with edge computing significantly reduces latency and backbone network traffic, enabling rapid processing and real-time data delivery. Introduction. The Internet of Things is rapidly advancing, connecting billions of devices that generate massive amounts of data at high speeds, necessitating low latency applications. Traditional cloud models face challenges due to centralized computation and storage in few data centers, which may not meet the real-time demands of applications due to the long distances from edge devices. Applications like Industrial Internet of Things, vehicle communications, and augmented or virtual reality require extremely low end-to-end latencies, often under a few milliseconds. The current IP-based approach, which relies on fixed servers, struggles to accommodate the high data volumes and latency requirements of emerging real-time applications. To address real-time service issues and enhance performance, the authors propose an open-source framework that combines NDN and ECC, leveraging their strengths to improve response times and reduce latency. The paper details several contributions, including a 7-layer entire architecture, a .NET Web API for communication, modifications to the NDN SIM codebase, the development of edge and cloud node applications, and the release of the source code for community use and enhancement. Background and motivation. Edge computing. Edge computing refers to technologies that enable computation to occur closer to data sources, reducing latency and increasing task execution speed by utilizing resources at the edge of the network. It focuses on performing data analytics near IoT devices rather than relying on centralized cloud data centers. Edge computing is often confused with fog computing, but they differ in focus. Edge computing emphasizes the proximity to devices, while fog computing targets infrastructure. Other related concepts include mobile cloud computing, which offloads tasks from mobile devices to cloud servers, and Cloudlet, a smaller cloud server that provides low latency processing for mobile applications. Differences between edge computing proposals. Edge computing concepts such as mobile edge computing, cloudlets, and fog computing differ in implementation and focus. MEC is specially designed to minimize latency by placing servers co-located with several cellular network-based stations, making it the preferred technology for future cellular networks. In contrast, cloudlets and fog computing facilitate task offloading, but they vary. Deployments environments with cloudlets are typically accessible via Wi-Fi in public spaces, and fog servers potentially located in private settings or as part of ISP infrastructure. Edge computing model targets different users bases and device densities. Fog computing is suitable for higher user and device counts, particularly in IoT and vehicle-to-vehicle communications, while cloudlets cater to IoT devices in public locations with a higher density. MEC primarily focuses on cellular subscribers and providers, leading to a smaller user base compared to fog computing. Additionally, the accessibility and range of communication technologies vary, with MEC leveraging 3G LTE networks, whereas cloudlets and fog servers use shorter range wireless technologies. Need of edge computing. The necessity of bringing content and services closer to end users comes from various factors that drive the evolution of edge computing paradigm. QoS and latency. While edge devices are capable, many lack the capacity to meet delay-sensitive requirements, particularly for applications in the Internet of Things like Wearable devices. Traditional cloud computing relies on wide area networks for accessibility, leading to delays and making it unsuitable for real-time and mobile applications that require quick computation and memory resources. Minimization of core network traffic. In traditional cloud computing, all device traffic must flow through the core network to reach cloud servers for processing and storage. This process can lead to higher response times and increased backbone traffic, especially as billions of IoT devices generate vast amounts of raw data up to 15 petabytes per month. Named data networking. NDN is a part of the information-centric networking paradigm, prioritizing content over host identification. Unlike traditional IP-based communication, NDN uses content names for data requests, enabling efficient content retrieval through interest and data packets. NDN builds on the earlier content-centric networking model, employing a three-tiered data structure. Content store for catching pending interest table for unsatisfied requests, and forwarding information base for routing interest packets. The main operational distinction is that NDN checks the PIT before CS to minimize lookup delays. When a consumer requests content, it sends as interest packet with the content name. Nodes process this request by checking the PIT, then the CS, and may forward the interest if the content is not found. Data packets returned to the customer include the requested content and additional verification information with routing and caching determined by specific policies. Related work about IACN over edge computing. There is a scarcity of studies focused on the integration of NDN with edge computing. Some works have proposed solutions for bridging IP and NDN networks, such as architectures enabling IP applications to communicate with NDN networks and gateways translating between NDN and IP packets. NFN extends NDN to edge computing by allowing the name field to interest packets to include both content names and expressions for named functions. However, NFN's capabilities are limited regarding the complexity of supported functions. To address this, Named Function as a Service (NFAAS) introduces unikernels, lightweight virtual machines that store functions in a kernel store for local execution, optimized through a scoring function based on function popularity. Recent proposals have sought to enhance NDN for IoT applications and dynamic computing at the edge. For example, NDNE extends NDN to support cloudification at the edge, enabling services like storage and computation to be identified using names. In contrast, the proposed framework aims to work effectively with both IP and NDN networks by utilizing .NET Web API services for user requests to reach edge and cloud nodes. Proposed framework. The proposed framework is structured using an N-tier architecture that includes three main tiers. Tier 1 representing things or end devices, Tier 2 edge computing, and Tier 3 cloud computing. Both Tier 2 and Tier 3 are further subdivided into layers, enhancing the framework's organization and functionality. The framework emphasizes the distinction between tiers and layers in the entire architecture, suggesting a need for clear definitions for effective implementation and understanding of the framework structure. Tier 1. Things or end devices. This tier consists of various end users, devices, and IoT devices such as sensor nodes and smart handheld devices, which indirectly request data and services and connect to the edge tier via a single hop. Tier 2 Edge Computing. This edge computing tier consists of fog servers that deliver low latency, delay constrained services to end users. Positioned one hop away from the things tier, it handles a moderate number of service requests, distinguishing itself from traditional cloud computing. Tier 3 Cloud Computing. The cloud computing tier is the highest level in the architecture and featuring traditional cloud servers with a substantial storage and computing resources. It is located multiple hops away from both the things tier and edge computing tier, resulting in higher latency for end users. Architectural details. The first tier of the architecture employs NDN, where IoT devices referred to as end user devices communicate using interest names to request content at the network layer. If tasks exceed NDN's capabilities, requests are forwarded to the edge devices. The producer node acts as a gateway between the NDN network and the edge node, maintaining a limited set of devices for end users. It processes incoming requests and either fulfills them directly or forwards them to the edge node for more complex computations. The framework exploits NDN's aggregation feature to handle identical requests from multiple users, reducing network traffic. This is facilitated by in-network caching allowing devices to access data from nearby nodes, thereby minimizing reliance on cloud computing and improving communication efficiency. To address potential bottlenecks in dense IoT environments, the framework allows for multiple gateway nodes. This ensures effective communication between end user devices and edge nodes, improving scalability and performance. The gateway node in this architecture operates on both NDN and IP protocols, enabling it to connect with edge nodes outside the NDN protocol when necessary. This hybrid functionality enhances the system's robustness and flexibility in handling various service requests. Results: interest aggregation in sparse environment. The experiment demonstrates that using NDN for interest aggregation significantly reduces the traffic forwarded to the edge node. In a simulated scenario with two customer nodes, 47.73% of interest packets were aggregated at the relay node instead of being sent to the edge node, highlighting the efficiency of NDN in managing request traffic. In contrast, when using a traditional IP setup with NDN, all requests from the customer nodes are forwarded to the edge node without any aggregation, leading to 100% of the traffic being sent. This illustrates the potential challenges for IoT environments where numerous devices generate high traffic, emphasizing the need for aggregation to avoid overwhelming the edge and cloud infrastructure. Edge versus cloud latency. The study measured latency performance of a cloud application hosted on Microsoft Azure and an edge application located in the lab using round-trip time as a metric. It found that the edge node, being only one hop away from the IoT devices, exhibited minimal latency, while requests to the cloud, which is multiple hops away, resulted in significantly higher latency. The results emphasize the advantages of edge computing for real-time applications such as augmented reality and virtual reality, as it provides lower response times compared to relying solely on cloud infrastructure. The minimal latency from the edge node, coupled with a short processing delay, makes it suitable for most low latency application requirements, while cloud reliance can lead to increased traffic and latency challenges. Conclusion: the proposed NDN-based ECC framework combines named data networking and edge computing to address challenges in real-time services. NDN provides network layer content caching, mobility, security, and interest aggregation, while ECC offers computation, storage, and caching close to end users, reducing latency and traffic. And extensive experiments with the prototype provided showed that integrating NDN with ECC significantly reduces backbone traffic and improves response times for edge and cloud services. Processing data closer to end users is essential for latency-extensive applications like AR and VR, as clouds cannot meet stringent latency needs due to their distance. NDN and ECC are thus promising for future networks. These are the papers that are referred in the research paper. Thank you for watching the video.